Yeah, so as I said before, what we will do is essentially look at how some of the concepts that we've covered so far can be applied. And in this particular case study, what we're going to be looking at is working with text data. Okay, essentially, we have a bunch of doctors' notes, notes about patients that they might have seen, and that they've written down. Essentially, the details of what they saw, what they prescribed, what tests they gave them, what are some of their clinical and non-clinical observations, and all that. And we have, let's say, we have a bunch of reports, essentially text data from different specialties, cardiology, neurology, radiology, and all that. Right? What we would like to do, let's say we have this data set, right? We have these bunch of nodes, but we don't have any other information about these nodes. Okay, and let's say we are interested in knowing, okay, which of these nodes are similar to each other, and the ones that are similar to each other might be from patients who have more or less the same disease condition, and it could be from the same discipline. For example, reports from neurology might be a lot more similar to each other than, say, report from gastroenterology and things like that, right? And we often come across data like this where we just have the measurements and we have no other information about what those measurements might or what sources those might be from. And in situations like that, we are often asking, okay, we have this bunch of data. Are there patterns in this data? Okay, given that we have no other information. So the first step in this type of analysis would be to find out if there are patterns. Once we are able to identify that some of these data measurements actually group together, a few other group here and a few other group there, then we might go and ask, okay, what might these correspond to? But the first step itself is asking what measurements that I've made actually group together, okay, or what measurements I've made or that I have actually cluster together. And that's essentially the problem of clustering. Okay, this is called an unsupervised learning approach. Learning, okay, which essentially means unsupervised means you have no other information other than just your measurements. So you have set of measurements, and these measurements for us will be a set like this, a bunch of n vectors, okay? Xi Rn, I itself goes from 1 to capital N maybe, okay, or maybe let's try. Okay, your measurement vectors are m vectors, and you have a capital N of them. Okay, and your goal here now is, for example, if let's say we can visualize these m vectors in m-dimensional space, it's possible that some of the vectors from here fall here in this m-dimensional space, a few others fall here, and then okay, if this was the case, then we would be led to believe in this measurements that I have, there are actually three groups of measurements, right? This is one group because all these guys are together, similarly here and here. And what I call a group is essentially this. If you take two members from the same group, they will be closer to each other than any other element from the other groups. Okay? So this distance would be smaller than any distance of this element to any other member in another group, and similarly here. Okay, this I would say. So here, if my data was actually distributed like this, then I'd say I actually see three clusters. Okay, and notice we can only say that is all we can say. We might not be able to say what this means. If you want to know what this means, then you might have to go to an expert and say, okay, I have these three groups, and these are the measurements we see. What do you think this might be? Okay, that might require additional experiments to then find out, okay, what does this mean? Let's say this is all clinical data. You might have to go and find out, okay, what might this cluster correspond to, right? But our problem right now is to see how do we identify these clusters if they do exist. Okay, um, I've drawn a clean cluster here. Often what you'll find is your data points are not that cleanly separated. If I draw it like this, if your data points are like this, then maybe it's not clear. You might say, okay, there I see one cluster here. Another person might say this whole thing is a cluster, or someone else might say, well, I think this is one cluster and this is another cluster. So there is obviously room for interpretation here, and there is really no one correct answer. Okay? Often what you will do is, in a clustering algorithm, you have your data, you have an algorithm that is able to identify these clusters. You'll say, identify n clusters for me, and it'll say, okay, these are the things I identify. And then you have to go back and then see if the clusters are well separated. And you might have to play around with how many clusters you identify and see how well you're able to separate stuff to identify clusters. Right? Um, so what we will do first is essentially look at the simplest of all clustering algorithms, talk about the algorithm, and then see look at an application of using this algorithm for clustering doctor's notes. Okay. So the data set I'm using is from Kaggle. All this is in the notebook, so you don't have to worry about this. Right. So the clustering algorithm that we look at is called the k-means algorithm. Okay. And k-means, to understand k-means, all we need to know is simply this idea of, all we need from the concepts that we've talked about is the 2 norm. What is the 2 norm of a vector? What is the definition of a 2 norm of a vector? Yeah. What is the definition? So if I had x that had x1, x2, xm, how do I compute the 2 norm of x? Yeah, it's sum of what? Yeah, that's all. Right? This is all we need for doing k-means. Okay. I'm essentially showing an example like I drew here. This is what you start with. And then if I asked you how many clusters do you see, most of you might say, well, maybe this is one cluster, maybe this is another one, maybe this is another one. And if you do k-means and you ask k-means to return 3 clusters, it'll essentially give you something like this, which looks like, okay, looks correct, right? I mean, of course, I've chosen an example where k-means works well. There are cases, of course, where it does not work well. And I've chosen 3 because I generated these 3 clusters myself. So I know that there are these 3 clusters that in the data. But in the real application, of course, you have no idea where this is from and how many clusters are producing that data. Okay. So in k-means, all you're asking is this. Well, this name itself probably gives you an idea what it is. In k-means algorithm, you have a bunch of data. You're asking for the algorithm to identify k clusters. Okay, and k-means essentially what it implies is the algorithm will return to you the k centroids of those clusters. Right. For example, if this was a cluster, right, the way I've drawn it, okay, let's say you run k-means on this data, and then it's identified these 3 clusters. Okay, the k-means will return to you the centroid, the average or the mean value of these points. Those are the k means. Okay, and what you're trying to do in the k-means algorithm is essentially you're solving a minimization problem. We we look at what this exactly means when we talk about optimization later in the course. But for now, we'll just mention this. So you're solving a minimization problem, and what you're trying to minimize is this. So you have the data. The user has given us that we need to identify k clusters. Okay, all you're trying to do is you're asking, okay, how do I find k centroids such that, okay, how do I find k centroids, and how do I find uh, so so you have cluster means, you have k cluster means, and because you have to cluster, and what clustering essentially means is you have these black colored points, and for each of these points you need to assign it a cluster number. You have to say what cluster does it belong to. So you need to identify the cluster means, and you have to come up with a cluster assignment. Okay? Where in cluster assignment, each data point in your data set will get a unique cluster assignment, and the cluster assignments will go from 1 to k because there are k clusters. Okay, so the k means needs to return these two. Okay, we need to have the cluster means and the cluster assignments, and the k means algorithm can be posed as a problem where you're essentially minimizing something like this: the square of the two norm of the difference between your data points and the cluster means. Okay, mj is the cluster mean of the jth cluster. Okay, and you are not just finding out the distance between the cluster mean mj and any data point, but you're finding out the difference between the distance of every data point I from the jth cluster mean, and not any data point, but these are points from the jth cluster. Okay, it's essentially this. Okay, you this is the first cluster, right? This is M1. Okay, you find the square of the distance of all the points in cluster 1 with respect to the first cluster mean. Okay, and you add them all together. You go to the second cluster. Okay, you find the distance of all points in the second cluster, square their distances with respect to this cluster mean, and then add them together. Similarly, you do that for all. That's essentially what this says. So the first summation goes over all the cluster means, or all the clusters k to 1. Okay, and the and you're finding the distance of data points from the cluster mean, and the data points you're considering are xi's, and I essentially comes from cj. Cj here is essentially your cluster assignment. Okay, so c1 will be a set of indices from 1 to capital N corresponding to the points that are in cluster 1. Let's say the x1 was in cluster 1, x2 was in cluster 1, x100 was in cluster 1, and then let's say only these 4 points were in cluster 1. Right? Then all you'd have to do is compute the difference of x1 with respect to m1, compute the difference of x2 with respect to m2, m1, x100 with respect to m1, and xn with respect to m1, and then take their two norms, square it, and add them all together. So as I said, the first summation goes over all the clusters, and the second summation goes over elements in each cluster. Okay, and you're essentially taking the sum of all these and 1 by n just to compute the mean. The mean measure of what is called a cost function, the minimization of a cost. Okay. So I've explained to you what that formula here means. What would be the interpretation of something like this? How would you interpret this? What are we essentially computing here? Yes, distance of what? Okay, this is in a way essentially a measure of, see, each of the inner summations, right? Okay, is this. Each of the inner summations essentially tells you a within cluster spread of points. Okay, if all points in cluster J, right, are very close to the cluster mean for the jth cluster, then this term would be, the inner term for the jth component would be small. Okay, so you need to identify a set of cluster means and a set of cluster assignments so that the the spread of points about a cluster mean is as small as possible. If you do that for all k clusters, then this whole summation would be small. So your problem then is to identify cluster means and cluster assignments so that this whole thing is minimized. That's essentially the minimization problem. The outcome of your minimization problem, minimization of the cost J cluster. So if you minimize J cluster, what you should get is a bunch of cluster means, and star means that's the optimal one. Okay, that's the best possible value for the J cluster means and J cluster assignments. Okay, where are my uh, k means of my clusters and what points in my data set correspond to which cluster, such that this J cluster is as low as possible and not lower. So it turns out, now if you think about how one would go about solving this, right? Okay, you could say, okay, then I have my data points. I'm going to randomly assign all my points to some k clusters. I'm going to assign it randomly. 1 goes to cluster 3, 2 goes to cluster 1, 5 goes to cluster 7, and all that. And then you randomly choose MJ, and then you say, I'm going to just search around to see what is the best possible set of cluster means and what is the best possible set of cluster assignment. It turns out this problem of minimizing this cost and identifying cluster assignment and cluster means together is not computationally possible. The problem is too big. Okay? Because my cluster means will affect my cluster assignment, and my cluster assignments might affect my cluster means. So it's a complicated problem to solve. So minimizing J cluster by simultaneously varying both Cj and Mj is a hard problem to solve. Okay, but what turns out to be a simple problem or a simpler problem is essentially this. Oh, there is a mistake here. Let me write down. So you have J cluster, which is like this. Right? Choosing both Cj and Mj is not simultaneously possible. Okay? But let's assume somebody's already given us the cluster means. Okay, I fixed the cluster mean. Okay, if Mj is fixed in this problem, it turns out you can actually very well solve. You can identify cluster assignments for your points such that this term is minimized. Okay, or if someone tells you that take this cluster assignment, 1 corresponds to 2, 2 corresponds to 5, 3 corresponds to 10, and so on and so forth. Once that is given, identifying the cluster means can be done very well such that this is minimized. Okay, and that's essentially the key to how k-means works. K-means, instead of solving this full complex problem, which is difficult to solve, it takes 2 steps. It starts by first fixing the mean. It says randomly fixes the mean, and then finds out for the given mean what is the best possible cluster assignment. Okay. Once you find the cluster assignment, you fix the cluster assignment and then go back and compute the mean again. That means you change the mean now, right? Once you've computed a new mean, you fix the mean and go back and compute the cluster assignment, and you keep doing this back and forth. And it turns out each time you do this, right? The very first time you start with some random cluster means, and you find out a cluster assignment and you compute this number. You'll get some value. Okay, let's call that J1. That's the first estimate. Once you've done that, you have a new cluster assignment. So you fix the cluster assignment, compute new set of means, and find the new cluster assignment. That will give you J2. And if you keep doing this, right, after a particular point, your J will actually converge. J will essentially not. One thing you're guaranteed with this approach is J will always decrease. Okay, and J will always converge to a value. That means after, if you keep running this over and over again, after a particular point, your Cj and Mj will not change anymore. They'll be fixed. That means that's the best you can do. Okay, and often it turns out that is also a pretty good optimal solution, the best possible cluster assignment and cluster means. Okay. So as I said, there are two steps here that I've listed here. The very first thing you do is you have your data set, you choose k random cluster means. Okay. So often what will happen is if you have your data points like this, for the very first iteration that you when you run this algorithm, you choose one of the three of the data points as your cluster means. So you might say these are my cluster means. Okay. Once you have the cluster means, you then ask, okay, what is the best possible cluster assignment? The best possible cluster assignment are, this is cluster 1. Okay, this is mean 1. Whatever point you have, whichever is closest to M1, or you compute the distance of all points with respect to M1, M2, M3. Okay, all the points that are closest to M1 than M2 or M3 would correspond to cluster 1. Similarly, for cluster 2, you find out the distance of all points from cluster 2. Whatever points have the lowest distance to M2 compared to M1 and M2, those would be cluster 2, and so on and so forth. So that's how you do the cluster assignment. Whichever point is closest to my cluster mean gets that cluster numbers. And once you've identified cluster assignment, right, you can update your cluster mean by simply taking the mean of the points that correspond to a particular cluster. Okay, if that is not clear, I'll run an animation and then maybe that will clarify it. So you keep running this over and over again, and after a particular point, Mj and Cj will not change anymore. Okay, they'll be fixed, and you stop at that point. Right. So this is what we started with. Okay, original set of points, and then initially you choose. I think I've randomly chosen here. Yeah, you choose a random set of points as your MJs. Right, the solid triangles are your initial guesses for the center, the cluster means. Once you know the cluster mean, you find out, let's say for the blue points, right? You find out all the points that are closest to the blue triangle than to the red or the green one. So those are all these blue points. So these blue points here are closer to the blue triangle than to the red or the green one. Okay, so you say these blue points now correspond to cluster 1, where blue corresponds to cluster 1. Similarly, you do the same thing for cluster 2, which is red, and you do for green, which is cluster 3. Okay, so you started with random cluster means, you did the assignment. Now the next step you do is, okay, now I have a cluster assignment, right? The cluster mean should essentially be the mean of these points. So you take these blue points, you forget about this triangle now. You take these blue points, you compute their mean. That means your blue triangle will now go to a different position, which will be the center of these blue points. You do the same thing for the red and the green clusters. Now you have a new mean. Now you go back and do the cluster assignment again, find all the points that are closest to each cluster mean, and you do this over and over again. So if you do that, right, the solid colored squares here are the final cluster mean, and the corresponding colored dots are the final cluster assignment. And the lines that I've drawn here are essentially the trajectories of your cluster means as you run this algorithm over and over again. Okay, and this plot here is essentially your J cluster as a function of the number of iterations. So you see that you started with some high value, and then each time you run this iteration of updating the cluster assignment and cluster mean, the J cluster drops, and then after 5 it does not change anymore because your solid squares essentially will stay at the same point. Okay, they will not move. Okay, that's the algorithm. Let's look at an animation to get an idea about how this works. Oh man, I didn't check this. Oh yeah. Yeah. Okay. So I have a bunch of points. I've chosen K to be 3. I want I want the algorithm to identify 3 clusters. Okay. J cluster is the current. Well, I should not have. Well, I should have done this. Where? The 3 solid dots that you see, those are the random initial cluster means that you've chosen. And the corresponding cluster assignments are shown by the colored dots. And if you compute the cost J cluster for that, you get about 285 something. Now, now that you have a new cluster assignment, you now recompute your means. That means each of those points will now shift. And now each of these solid squares, right, is actually the mean of the orange square is the mean of the orange circles. The blue square is the mean of the blue circles, and so on and so forth. Now that your means have moved, that means your cluster assignment can also change now, right? So you do the cluster assignment again. It's not changed. If I keep running this, that's it. So after this point, nothing changes because the blue circles and the cluster assignments have kind of converged to a point where nothing changes anymore. Now, if I just start from a different set of random initial positions, yeah, if I start from here, right? So you see that they essentially move to a point where the cluster means and cluster assignments kind of converge. Let's do another one. Yeah, this is a nice one. So with each time we run we've assigned the cluster, and if you now recompute the means, they move. You do a new cluster assignment, you should see that the colors of the circles actually change. Some of them will become blue to green, blue to orange, and so on and so forth. You update the means, you redo the clustering. So you see some of the orange points have now become green. You redo the mean computation, and if you continue this, they'll essentially now converge. Now, no matter where you start, it turns out all the time they'll essentially converge to this. That is specific to this data set. Okay, I've chosen the data set in such a way that the k-means kind of converges to the same solution no matter where you start. Now, instead of doing 3, right? Let's say I asked for 2 clusters. Okay, now I want the algorithm to identify 2 clusters. That means that you initially choose 2 cluster means, and then you do the computation again. Now you will see that each time, so when we started where we started in this case, you get these 2 as clusters. If I start from a different set of positions, there. Remember the previous solution from the clustering algorithm? Look at this. In the previous one, these were identified as a single cluster, and this was identified as another cluster. But in this particular case, because we started at slightly different position, these are now identified as a cluster and the bottom ones, right? So this can happen with k-means. What will happen if I only say I want one cluster? I want k to be 1. What will happen? Yes. All it will do is assign everything to as one cluster and compute its mean, and it's done. So if you say k equals 1, the algorithm will stop after the first trial, after the first iteration. That's it. So no matter where you start, everything gets assigned and you compute the mean. That's it. Now, if you can of course go crazy and say, okay, I want 5 or even worse, 9 clusters, because you don't know how many clusters there are in your data, right? If you do this, it'll do the same thing. Start. Now, of course, interpreting this becomes a little more difficult because the more clusters you have, of course, it will always identify how many ever clusters you want, but they might not have a lot of meaning. Okay, So that's one problem with your you choosing K. You have to be careful about how you choose K. Right? Right? And each time your K-means algorithm is essentially trying to minimize this cost function. Is it possible for this? See, because this is a mean of a set of distances, is it possible the lowest possible value for my cost is 0? Is it possible for me to get 0 cost? What would 0 cost correspond to? Yes, very good. Yes, that's correct. Okay, so what does it mean about how many? What should you choose your K to be for to get 0 cost? Or is it possible for me to choose a K so that I get 0 cost? Yes. If you choose K to be capital N, essentially there are K points here. Each one will move and essentially go to one of those points. Okay, but that is of course useless. If you have K points and you identify K clusters, it's really not useful to anybody. All right. So that's all I wanted to say about K means. We'll now go to the actual data. Okay, so that's in case study 1. Let me open it. You can open it on your computer as well. I don't know how visible it is here. This is probably better. So if you simply run this, it'll so to execute this, you should run all the cells one after the other. Run this. Okay. And you need to download the data from Kaggle and then put it in a specific folder. So basically this data/case study 1 folder. And after you've done that, if you run this, it'll tell you whether or not you have everything to run this notebook. If you don't have the data, it'll say failure. And essentially that means it's not finding the data that it needs to have. Because I have the data, it says, okay, it's success. So the data set that we have is a CSV file. Okay, CSV file is essentially a tabular data format with rows and columns. Rows are in a separate lines and columns are separated by commas. This particular data file has 2 columns: medical specialty and report. Okay, we only need the report for our for this particular case study. Okay, medical specialty is essentially what discipline it is from each of the reports, and the report is some clinical report that was written by a clinician. Okay. Now, as I said, our goal now is to see if we can cluster these reports together. Okay, and we want to apply the k-means algorithm. But once I say that, you probably immediately see the problem that for running the k-means algorithm, the data that we need should be a bunch of n vectors, right? Or m vectors in this case, right? But what we have is text, right? You cannot do this with text data. So then the question is, okay, how do we work with this text data, given that these are not real numbers? There are many ways to address this issue. One approach that we've taken in this particular case study is you take the text data. It's a string. Okay, if you load it in Python, each report will be of type string. We need to essentially convert this text data into a m vector. Okay, and the conversion has to be such that this m vector captures whatever relevant information there is in this text data. Okay, I mean, what is relevant to you might depend on the application, but in general, because we are talking about clustering these text reports into different clusters, we want to make sure that whatever information there is in each of these reports that distinguishes one report from another, that is captured by your m vector. Okay, such that when you convert your text to this M vector, and after that you will essentially only work with this M vector. This M vector is supposed to contain whatever information you are looking for or you're interested in your text data. There are again many ways to do this. One common approach is called this count vectorization, which essentially is this. You have your text data. In addition to this, let's say we have a bunch of keywords, okay, or tokens, right? A set of medical terms, okay. Let's say an expert has given us, saying these are all important terms you should be looking for in a report to get an idea about what specialty it might correspond to. You have this bunch of keywords. What you do in count vectorization is very simple. Let's say you have, let's say, M keywords. Okay, you take a report and you count. So you go from keyword 1 to M. You take the first keyword. You count the number of times in the text keyword 1 appears. Okay, and then you put it here. Let's say it appears 4 times. You look at keyword 2 and see how many times it appears. Let's say it did not appear. It's a 0, 1, 5, 0, 0, 1, and so on and so forth. So you are essentially counting the number of times a set of keywords appear in your text, and that is how, or this is the count vectorization approach, and that's essentially what generates our M vector. And from this point on, we won't work with the text, and we will assume that this contains all the information that we need for the clustering problem. It's possible this is a bad approach, but we'll have to try and see. We don't know a priori what is the best approach to convert our text to a bunch of M vectors, with the ultimate goal of finding clusters or grouping reports that are similar together. Okay. So, for example, let's say you had a text like this, which you wanted to convert to an M vector, and then the tokens you had were quick, brown, fox, lazy, and dog. So if you do this count vectorization, the 5 vector that you would get would be simply this 2, 1, 3, 2, 3, which basically means quick appeared twice in this text, brown appeared once, fox appeared thrice, lazy appeared twice, and dog appeared thrice. Okay. So we then read the data file, and the data file essentially looks like this. You have a medical specialty column, and then you have a reports column. We will only work with the reports column. We will not worry about the medical specialty, because we are assuming that we know nothing about these reports, even though in this data set we have, okay, because we are doing a toy exam. Right? And so this data file essentially has 273 reports from radiology, 200 from gastroenterology, 300 from cardio, 200 from neuro, and there are lots of surgery ones, okay, like 1,000 of them. So in the rest of this notebook, we will essentially remove surgery, because surgery has 5 times more data than the other specialties. Any analysis you do will be strongly biased by surgery. So for the rest of the notebook, I've essentially removed surgery. So we will essentially not use any data from surgery, and we'll only use these 4 disciplines, which gives you around 1,100 reports. Okay, what's that? Okay. First thing we do is, if you look at the report, right, there are words, there are capital letters and small letters. We don't care whether cardiology starts with a capital C or a small c, right? So we first convert all our reports to lowercase, okay, and create a new column, which I call report lower, and we'll essentially now only work with this. Once you have these reports that are converted to lowercase, you then apply a set of keywords. Okay, the keywords information is in another file, okay, called token dash some number dot text. If you open this, yeah, so it's essentially a text file with each keyword separated by a comma, and this is essentially what we'll use for generating our M vector. There are 50 tokens here. That means every report will get converted into a 50 vector. Okay, so you read it into a list, and then I've written a function to essentially count the number of tokens. I've written the function. See, there is a natural language processing library in Python, which of course you should actually use if you're doing real application. But for the purpose of the course itself, if it's a simple enough function, and then I would encourage you to write it yourself so that you have an idea about how it's done. Okay. Later on, if you're working with the real problem, you should, of course, use the library and not write your own code if it already exists in the library. Okay. So I have a simple function that counts the number of tokens. Then, if I now run each of these reports through this count vectorization function, I'll get a 50 vector. And that's essentially what I'm showing here. I've randomly selected 10 reports, and this is the 50 vector corresponding to each of those 10 reports. Okay, you see that a lot of them are 0, which is understandable. Maybe these keywords only appear in specific reports from specific medical specialties, and not all of them. And from this point on, we will essentially only use these 50 vectors for doing the clustering. The clustering also, I've written my own k-means, but later you should, for a real application, use scikit-learn's k-means. But I would encourage you to go into the code and look at how it's written, which will essentially be these two steps of updating cluster assignment, cluster mean, and going back and forth. Okay, so that you get an idea about how the algorithm is actually implemented. Right. So here I say I want 4 clusters, and then I give a bunch of other parameters which you can go into the details when you look at the code yourself. And then if I run this, the first thing I'll look at is my J cluster. Okay, so this is the plot. So this algorithm has run for 10 iterations before it essentially said there is no change in the clusters anymore, and the J cluster essentially dropped like this. Now, if you go in, now we could ask, okay, we have 4 clusters that are generated by my k-means. If you had no other information, right, it would be very difficult for us to know are these clusters meaningful. That means, for example, if you look at the reports from cluster 3, do they look all similar? For example, you could ask expert to look at those clusters and say, okay, do you think these correspond to the same medical specialty? So that's how you obtain feedback. But in our case, we do have a column called medical specialty, right, which we chose to ignore for this problem. Right? What we could ask, okay, we have our k-means algorithm, which has identified a bunch of clusters. We could now go back and look at the medical specialty column and see if the clusters that are identified actually come from one set of medical specialty. Right? For example, I have 4 clusters. I have 4 clusters, right? Let's say I take cluster 1 and I look at their corresponding medical specialties. If most of them come from, let's say, cardiology, then I'd have confidence in this cluster saying, okay, this cluster 1 probably corresponds to cardiology reports. And similarly for 2, 3, and 4. Right? On the other hand, if I look at these clusters and each of them has equal number of reports from all different disciplines, then you would say, okay, not a very good clustering output, given that our ultimate goal was to cluster these into reports from similar medical specialties. Right? So the k-means, so you have your 1000 reports. If you run the k-means will give you the cluster assignments for these. Okay, you now get all the reports corresponding to cluster 1 and then look at their corresponding medical specialty. This is medical specialty, this is a report. You take all cluster 1 reports and look at their corresponding medical specialty. Okay, and count how many radiology reports, neurology reports, cardiology reports are in cluster 1, cluster 2, 3, and 4. And you can generate a summary like this. And when you do this, this is what you find. Cluster 0, which is essentially cluster 1. I'm not using cluster IDs from 1 to k. I'm using from 0 to k minus 1. Cluster 0 has essentially hundreds of reports from all 4 disciplines. Okay, so not very good. It looks like cluster 0 is not conveying a lot. It's not really separating stuff up. Similarly, for cluster 1, there are more or less the same proportion of reports in each of the 4 from each of the 4 specialties. But if you look at cluster 2 and 3, right, There are, of course, not many uh, reports that go to cluster 2 and 3, but whatever goes to cluster 2 appears to be mostly from gastroenterology. Okay? Similarly, whatever goes into cluster 3, in fact, appears to be entirely from cardiology. So our clustering has not worked very well, which is what you'll often find with real data as well. With a very simple approach like this, most things will not yield the kind of results that we're looking for. So you'll have to do something a little bit more sophisticated. But at least with using a bunch of tokens that somebody has given us, and by converting them into n vectors and doing k-means, looks like cluster 2 and 3 kind of pick up reports that mostly correspond to gastroenterology and cardiology. See, and there are many reasons why this could be, right? It could be that our tokens are really useless, right? So, for example, if you choose bad tokens, of course, you will not identify anything useful, right? For example, if my tokens were all articles from the English language, right? Then all reports will have articles. That means you'll essentially have all four or how many ever clusters you identify have reports from all different disciplines, right? So the choice of the token itself is very important. And maybe just looking at individual tokens is not enough, right? You might have to look at maybe pairs of tokens that appear together in a report, or something more sophisticated than that, right? That could be an issue. Maybe k-means is not the right algorithm, right? Or maybe k was inappropriately chosen. But at least we know k is 4, right? Because the 4 of them, we know that the data that we got was from 4 different specialties. So in this case, that is not a problem. But in a real application where you don't know k, that could be an issue. Right? So you'll have to kind of play around, try different approaches to see what you get. And at the end of it, if you're saying, I have a robust algorithm that will actually cluster new reports that will come in, it's not enough that you fine tune an algorithm that works only for your current data set, because you might have fine tuned it so well that it works only on this data set. If I give a new report, it might actually cluster it very badly, right? So you'll have to take into account that issue as well if you're developing algorithms like. Right? So all that could have gone wrong. Okay, so those are all things you should be aware of. Or maybe what did I miss anything? No, I think that's it. Okay, we'll look at one last thing before we proceed, right? So we know k-means returns two things, right? The cluster means and the cluster assignments. Okay. And we used 50 tokens. That means we get a 50 vector. We can plot the 50 vector. I mean, we cannot visualize it as a vector in a 50-dimensional space, but I can plot them like this, right? The x-axis corresponds to the 50 indices, token 1 to token 50, and the y-axis is the value of corresponding to each of those positions. And I'm essentially plotting the 4 cluster means. And what we find is this, right? If you look at the mean for cluster 0, right? Remember, cluster 0 had reports from all disciplines, right? If you look at the mean value, right, it's essentially close to 0. What does that mean? What does it imply? The mean the centroid of cluster 0 is essentially all 0, which means that my tokens are actually not very good, because most reports don't have these tokens. Okay. So that would be the interpretation of this being all 0. And in fact, for token cluster 2 also, most of them are 0, and maybe a couple of them are slightly above 0. So these two tokens appear, but the rest of the tokens never appear in these reports. But if you look at 2 and 3, right, again, most of them are 0, which essentially tells you now that our tokens are probably in a not very good, or not chosen properly. But if you look at cluster 2 and 3, right, cluster 2 has mostly very small values for the token values, but it has a relatively large value for some token which is, I think, ladder. I don't know what that is. Okay? And the reason it's essentially picked out reports from gastroenterology, which that's cluster 2, it's because this term ladder appears in those reports, right? And it appears a lot of times, right? And that's essentially why these 21 reports from gastroenterology got clubbed as one cluster. Similarly, for cardiology, the cluster 3 assure and ending, these two terms appear a lot of times, and those 18s got clustered into 18. So it's possible now. So what the interpretation of this would be, if we had chosen our tokens correctly, maybe we could have found better clusters than what we've done so far. So you can use this information then to see, okay, what approach do I use? Maybe you have to go back to a clinician and ask them, okay, can you give me a better set of keywords that we can use for clustering new reports that come in? All right, so that's essentially the first application that I wanted to talk to you about. And each of these case studies will have assignments which you'll have to then solve and submit, which will basically be questions related to concepts covered in that case study, or you rerunning the analysis using a slightly different approach. I would encourage you to reuse the code, look at the code, modify it to your needs, and reuse it as much as possible. And the assignments in this particular case, assignment one, if you remember in k-means, right, you start with random locations for your initial means. And it's possible, depending on where you start, you might get a completely different cluster assignment. Right? So first thing you have to make sure whenever you're doing k-means is to see that your algorithm is robust to your initial choice for cluster means. Right? For example, in the animation that I showed, if you choose k equals 3, no matter where you start, it looks like the cluster means will always converge to the same set of same position and the same cluster assignments. But if I changed k to a different value, each time I run this, I get a different set of clusters. So you don't want a situation like that. You want to make sure that your clustering is not sensitive to your initial choice of cluster mean. Okay. So what people will do is when they use k-means, they will run k-means multiple times and then ensure that the clustering that they get, the clusters that they're getting result, or you get the same cluster no matter where you start. Okay. So you need to do something like that. So I've only run it once. You'll have to run it multiple times and then see, at least roughly see if this pattern appears. For example, it's possible if I started from a different set of initial positions, right? It's possible I would get beautiful clustering, right? Uh, Maybe cluster 0 will be gastroenterology, cluster 2 will be cardiology, cluster 2 is neurology, and 3 is radiology. We don't know, right? So you'll have to do that. So the first assignment is for you to rerun this analysis by starting at different initial positions. And the second one is about the tokens. So I've used the token 10.txt file. You are now required to use token 25, which will now give you even larger set of tokens. We used 50. This one has 125, and see if that leads to better results. And the third one is you play around with k. We said, I've used k as 4 because we knew it came from 4 specialties, but you play around with k equals 2, k equals 5, maybe k equals 6, and see what you get. Yeah? So that's what you need to do. Okay, that's all about case study 1. Are there any questions before we proceed to very quickly discussing application of matrices and then the next case study? If you have any questions, we can discuss it now. No? Okay. Okay, before we look at the next case study, right? We'll now quickly look at some situations, some applications of matrices, where matrices and set of linear equations come up, and they're useful. Okay. We look at 4 applications. The first one is, of course, linear electrical circuits. I won't go into the derivations. You can do it yourself. I'll only roughly point out where these things come up. For example, if you can extend these to circuits with capacitors and inductors as well, linear components. No, that's not what I want. We'll do something more relevant to with some biomedical application. Okay, let's say we had an electrical network like this. The horizontal resistors are all R1, and the vertical ones are R2. Okay, and we've got two nodes which are connected to a current source. Okay, that means you're injecting a current I here, and you're taking current here. Okay. If we had a situation like this, and we have control over I, we determine I. Okay. We want to solve, if this is set up, right? If these are my I's, we want to solve for the voltages at these 8 nodes, V1. Let's say I'll name these nodes 1, 2, 3, 4. Each of these nodes has a potential V1, V5, and so on and so forth. What we want to know is, if we have a specific current that we are supplying to this network, what is the corresponding V vector? V vector is essentially the voltages at these different nodes, V1, V2, V3. Yeah. So we want to solve for this. And it turns out that this will actually be of, if you write down the node equation for each of these nodes, okay, using Kirchhoff's current laws, what you will end up getting is something like this. You will have, there are 8 nodes, you will have you'll have 8 equations. Okay, I mean, you can make them less than 8, but we won't worry about that because we've identified 8 nodes. We'll have 8 equations. You'll end up with an expression like this. This will be from R8, this from R8, and this will be, okay. This will essentially be involve terms with R1, R2. This will have terms that will essentially be a bunch of zeros or i's plus I or minus I. And this V will be your set of unknown voltages, okay, that you're trying to solve for. Okay. Okay. An area where this is applicable is, imagine now, well, I'll just draw here. Right? You've got somebody's arm, okay, and you've got a bunch of muscles here, and some nerves, and then some fat tissue and all that, okay, the bone and all that, right? Uh, I mean, an area of research or clinical use is the use of electrical currents, external electrical currents that are passed through the body to essentially activate paralyzed muscle. Okay. Now, let's say you have uh, a muscle that is lying somewhere inside my arm, and I want to activate that muscle by essentially passing current externally from the surface, right? And I want to know, okay, where do I place these electrodes? And how much current do I send if I want to activate the muscle to some extent? And let's assume activating that muscle requires some distribution of potential in my body. Okay, the potential has to be distributed in space inside my body in a specific way for me to activate that muscle. Okay. Then the question is, how do I choose my eye and my electrode locations so that I get the distribution that I want? Okay, this is exactly applicable here. Okay, now let's take a 2D example. Let's not worry about making this a 3D example. Right? Let's say this is the region of body that we are interested in. If you think of it as a rectangular region, okay, it's got different types of tissue as you go from top to bottom, and in this side. In the center, maybe there is a muscle, there is a bone, and then on top of it there is, say, muscle, and maybe bottom of it there is muscle, and then there is your skin, and then there is some fat tissue here. Let's say this is this is the composition of my arm, right? One thing you can do is, let's say we have this model from a CT. Okay, you can divide this into rectangular regions, and each region, depending on what tissue is there in that region, we know the resistance properties of the tissue. That means we know the resistance in the vertical direction and the horizontal direction. Let's say we've characterized that already. We know that property for fat, we know that for muscle, we know that for blood, skin, and all that. If that is the case, if you had the CT image, right, you can actually generate an electrical network like this with different values for R1, R2, and stuff, and you will have a huge electrical net, depending on how many pixels you've generated. And now you want to know, and let's say you have electrode of a specific dimension. This, or even better. Or let's say we have the ability to inject current anywhere on the surface of my arm. That means I can inject and take out current anywhere, but the only restriction is the sum of all these currents has to be zero. Whatever goes in comes out. And I want a specific, let's say this is the region of my muscle, and I want a specific set of voltage distributions along the muscle. Okay. Then you could ask, what value should I choose for my currents so that I get the voltage distribution that I want? Okay. So if you had a model like this, you can actually pose this problem like this and then solve it. The only difference is it will be the other way around. So here I is known and we are solving for unknown voltage. For this problem, what you will have is this. You'll have a R matrix. So this is a matrix of conductances. This is a matrix of resistances. You want to solve for I to get a desired voltage distribution in this network. Okay, that's an area where you'd have your, well, you have the use of matrices to represent this problem, and you'd use your whatever methods we have for solving linear equations to solve for something like this. Right. So that's one area where these become useful. And the next one is something that we saw in our introductory lecture. Something that we do in the lab as well, basically application in robotics. The one, why? So this is of length L1 and L2. How do we compute, given that we know L1, L2, theta 1, theta 2, and this, let's say this is the shoulder, this is the elbow, that's the hand, and we assume that the shoulder is at the origin. How do we compute the position xp and yp of the hand with respect to the shoulder? Well, you don't have to derive it. I will write it down. So xp will simply be L1 C1. I'll say what C1 is later. C1 to yp will be L1 S1 L2 S12, where C1 simply means cos theta 1 and C12 means cos theta 1 plus theta 2. You can verify that this is correct later on. Okay, I mean, we've discussed this clearly. It's not a linear relationship. The relationship between theta 1 and theta 2 with respect to xp, yp is nonlinear. Okay, but if you take the time derivative on both sides, right, of both these equations on the left and right hand side, you have xp dot. That's the time derivative. Also notice this before to make it more explicit, right? L1, xp and yp are functions of theta 1 and theta 2. Okay, let's say theta 1 and theta 2 are changing with respect to time. That means xp and yp will also be functions of time, right? So that means I can take, let's say I have xp of t. I can take the time derivative of this, which I will represent by xt dot. and I'll drop the explicit dependence on time. On the right hand side, because theta 1 is a function of time, if you take the derivative on the right hand side, what you'll have is this. You'll have L1. You first take the partial derivative of C1 with respect to theta 1, and then the partial derivative of theta 1 with respect to time. Okay, that will give you the derivative of this with respect to time. Okay, what is the partial derivative of C1 with respect to theta 1? It's minus sine theta 1 and multiplied by partial derivative of theta 1 with respect to time, that is theta 1 dot. And similarly, if you do this, you will have L2, you will have S12, and there are two terms now, theta 1 plus theta 2. Both are functions of time. So you will have theta 1 dot, theta 2 dot. And if you rearrange these, what you will have is this. It will be minus L1 S1 minus L2 S12 theta 1 dot minus L2 S12 theta 2 dot. Okay. And similarly for Yp, can you tell me what will be for Yp? It will again be functions of theta 1 dot and theta 2 dot. What will it be? Well, first partial derivative of this with respect to theta 1 and then with respect to time. So that will give you L1 C1 plus L2 C12 plus L2. Okay. Now, if you fix the value at any given value of theta 1 and theta 2, right? This is a fixed value. These four terms are fixed values, right? It means for a given theta 1 of t, theta 2 of t, the relationship between the velocities of the endpoints and the angular velocities of my joints is in the form of a set of linear equations. Right? This is B1 equals A11 x1 plus A12 x2. Similarly here. So for any fixed value of theta 1 and theta 2, what you have is xp dot and yp dot given by, what will be the four terms here? What will be the size of this matrix? 2 cross 2. It's mapping from 2 vector to 2 vector. So it has to be 2 cross 2. What are the four elements here? Yeah, what is the first element? L1 S1 minus L2 S12, L2 S12. Yeah. That means for a fixed value, right? This is a fixed matrix, which is usually represented by J, and it's called a Jacobian matrix. What this means is this, okay? Let's say my arm is in this posture right now. It's like this, okay? And I want the endpoint to move with the velocity like this. This is my desired velocity vector. I want the endpoint to have a velocity vd. Okay, I can ask, how should I choose my theta 1 dot and theta 2 dot so that my endpoint is moving with this velocity vd? That means this is your vd that you're interested in. You fix theta 1 and theta 2. You're asking this question for this particular posture. And this is your unknown. If J is invertible, okay, J is full rank, then in fact you can solve. You can solve for any velocity vector that you want. If J is not invertible, then of course you cannot solve this. Well, it depends. You might be able to solve only for specific cases. For other cases, there is no solution. Okay. So this linear relationship applies even for a nonlinear problem like in robotics, but only for a fixed posture. If the arm moves to another posture like this, then this J matrix will change. Because this J matrix is a function of theta 1 and theta 2. So for a given value of theta 1 and theta 2, this is a fixed matrix. But if the arm moves, then this now is a new matrix. Yeah. So it's linear in a fixed posture, but overall it's still a nonlinear problem. Okay, so that's the second one. Third one, again, I'll go through it very quickly. We will consider a simplified situation. Say we have an X-ray source. This is at the origin. Call it Y. This is X. And let's say this X-ray source actually emits X-rays in a cone like this. Okay. And then we have a detector. Okay. There are a bunch of detectors here. Okay. And let's say this, we know this cone angle, the maximum possible cone angle is given by the max. It's got different rays that come out at different angles, but the angles of each of those rays is between minus theta max and plus theta max. Let's say I have a small rectangular body somewhere in this region, okay, and it's at some location x naught, y naught, and the length and widths are dx and dy. Okay, and we assume that this body has uniform absorptivity, right? The coefficient of absorption of X-rays is uniform, right? And let's say we call that alpha. Now, if you have a body with absorption coefficient alpha, and if you have, let's say, an X-ray of intensity IS enter the body, it'll move in a straight line inside the body, and then it'll come out, and it'll have some intensity I naught. Some of it is lost inside because it's absorbed by the material in the body. Right? It turns out IS is related to I naught is related to IS, and this alpha and this distance d. Okay, through this relationship. Okay, the absorption coefficient multiplied by the distance it traveled in the material with absorption coefficient alpha, e power minus that, and then multiplied by your original intensity gives you this. The relationship between alpha and I naught, let's say IS is fixed. Relationship between alpha and I naught is nonlinear. Okay, but because we know intensities are always positive, and we'll of course assume IS is not zero and I naught is not zero. Okay, then if you rewrite this whole thing like this, right? We'll bring this down and take the natural logarithm on both sides. What you will have is this. Okay. Now the relationship between the left hand side and the right hand side, if in terms of alpha is linear, or this and d is linear. Okay, and that's essentially the key for how we can use again a set of linear equations to work with this problem. Okay, all right. With that, now say we have some small body here with a fixed coefficient of absorption in some location in space that falls in this region where the X-rays are being shot out between the source and the detector. And let's say we are interested in this particular beam that goes through and comes out. And we'll assume outside of this region, right? Um, there, let's say rest of it is air. So there is no drop in the intensity of the X-ray anywhere else except when it goes through this body. Right? And we'll call this theta. Okay? This particular ray at an angle theta. Okay? And let's say the source intensity was IS. Now the question is, what will be, and let's say that source gets detected at this point, and the intensity that's detected is ID. Okay? The question is, what is ID? How would you find out ID given that you know x naught, y naught, dx, dy, and alpha and theta? Okay, because if I give you, if theta was here, right, then you know ID equals is because there is nothing to absorb it. If theta was greater and the ray was here, there is nothing to absorb it. ID will be is. Okay? So how would we solve this? How would we find out ID? Take a guess. What do you think? Well, first thing we need to make sure is for a given x naught, y naught, dx, dy, and theta, we need to find out whether or not the X-ray passes through the material. How will you find out if it passes through the material? Well, you can do this. Well, you know the equation for this line, right? The X-ray line. What is the equation for the X-ray line? Let me write it there. Well, I know the slope of this line, right? Slope is essentially what in this case? Tan theta, no? Because this is my x, this is y. I know theta, so my slope is tan theta. And let me say I call that slope m because I know theta, because I know which ray I'm interested in. I know my slope, which is semi-clean tan theta. So that's fine. This I know. Okay, that means I know the equation for my X-ray. The X-ray equation is essentially right y equals mx. Now, how do I find out whether or not my X-ray passes through that region of interest? Well, you essentially find out the intersection of your X-ray with respect to 4 lines. Your X-ray will intersect these 4 lines, right? Except for when theta is 0, it will never intersect with these two vertical lines. Or yeah, these 2 lines that are parallel to the x-axis. But for any non-zero theta, this X-ray will intersect all these 4 lines, and you will have to find out where those intersections are, and you have to ensure that the intersection points actually fall within this, okay, or at least on the boundary. Okay, if I had an X-ray like this, right, it will intersect these 2 points, but the points of intersection will not be on this boundary. So that's essentially what we need to find out, that the intersection points fall on this boundary, and we need to find out those points, these 2 points. Okay, I'll call it point 1 and point 2. Those 2 points are important because the exact locations of these points will tell me the distance covered by the X-ray within the body, right? Because it will essentially be the Euclidean distance between these 2 points, right? So I'll give you the steps. I won't do the derivation. So you need to identify. So next thing, so this we know. Second is identify if 1 and 2 are on boundary of uh, the body. If it's not, then you have not, you know, ID equals IS, then you're done. But if it does fall on the boundary, then you have to then find out the entry and exit points. Okay. Uh, let's say we call it P1 and P2. These are the entry and exit points. If I know these 2 points, then I know the distance that the ray travel inside my body, which will simply be d, which is equal to P1 minus P2. That's the distance. Okay. If I know this, then I know what my detector will pick up. Right. My detector will essentially pick up d will be equal to, will depend on the intensity of the X-ray that entered the body multiplied by, I know the coefficient of absorption for the body, or d. Okay. Is that clear? Okay. Now, in a real situation, of course, the detector is not continuous. There are discrete detectors that are placed, right? So you maybe have, okay, and you don't, the X-ray source is not sending out rays in all possible values for theta, but it's essentially sending only rays that will essentially end up in each of these detectors. Let's say there are m detectors. Okay, that means I have m possible rays to consider. Okay, this equation that I have is for a single theta. So in fact, this is a function of theta, and this term is a function of theta, right? Or let me just call it d. This is d of theta, right? If I have a situation like that, and I have a small body that is at x naught, y naught with dx dy, and I shoot m rays and I pick up the outputs from my detector, what I'll end up having is essentially d1, let's say di essentially corresponds to d of theta I. Okay, and I goes from the m rays corresponding to m detectors, right? That means I will have, for any one shot of these m rays, I'll have m measurements because I have m detectors, right? My measurements, let's say, will be I d of theta 1, I d of theta 2, I d of theta m. Okay. And each of these will be determined by this. Okay, is multiplied by minus e power minus alpha times this distance, if the ray passes through the body. If it does not pass through the body, then you can simply say d of theta is 0. Okay, so this d of theta, the distance traveled inside the body, will be E1 minus P2 if X-ray passes through the body, else it will be 0. That's your d. Okay, because if you put 0 here, then you get ID equals IS. That's what will happen. Now, each of these will now be IS e power minus alpha d1, IS e power minus alpha d2, and each of those d's is given by this. Again, a nonlinear equation, but if you convert it like this, because we know IS, right? We know d1, d2, dm, and in this particular case, what we don't know is your alpha. We don't know the absorptivity of of this material, and that's what we're trying to find out by shooting out X-rays and getting a bunch of measurements to estimate alpha. So you'll have alpha dm. If you take these to the denominators and take the log and stuff, what you'll end up having is a set of linear equations like this that will look like this. So this will be minus d1 minus d2 dm, and on this side will be the natural log of I d theta 1 by is, and let's just call that delta I1, delta I2. Yeah, is that clear? Now, let's say you don't know alpha, you shoot m X-rays, pick up the intensities measured by your detectors, and you know that there is a body at x naught, y naught with size dx dy. What you don't know is its coefficient of absorption. If you take these bunch of measurements, you know this side because this is from the geometry of the problem. This is from geometry. These are measurement. Geometry essentially says the physics of the problem, right? Where is the source, where are the detectors, and where is my body? These are a bunch of measurements, and this is the parameter that for the parameter of the body that I'm interested in. So this is essentially an example of an estimation problem. Okay. This is if you have a small body with a fixed with constant coefficient of absorption. What if you had a situation like this? You had the source, you had the region over which you're passing X-ray through, and let's say you had a body like this with varying coefficient of absorption. It is not a fixed coefficient of absorption. Of course, the variation is continuous in space. Because we are trying to solve this using a computer, we will then say, okay, we will divide this into small regions. And the regions are small enough that you can assume the the coefficient of absorption in each of those small regions to be fixed. Okay. Now, each of these points, right, is essentially an example of this problem, right? So now, when you just had one pixel like this with a fixed coefficient of absorption, you had something like this. A column vector multiplied by a scalar gives you a column vector of measurements. But now you don't have a single pixel. Let's say the number of pixels is you've divided this into n rows and n columns. You have n square pixels. We'll stop here after this. N square pixels. That means you have now your alpha is an n square vector because you don't know the absorptivity of each things, right? And you can use this simple problem to essentially then build the equations like this for this problem. And what you'll end up having is this. Your alpha now is n square vector. Measurement is still just m, right? So you have your, let's say, I, which is the m vector, okay, which will be now go through, let's say, a D matrix. What will be the size of this D matrix? Yeah, you should not take so much time this late into the course. What is the size of the D matrix? Well, the D matrix multiplied by n square vector gives me a m vector. So what is the size of the D matrix? Yeah, n cross m. M cross n square. Okay, and you can derive the expression for this matrix by essentially doing the geometry here. There is one complication. Here, the source intensity was is, so we could safely assume that the at the entry point, the intensity was is. But that's not the case here. Now, if I have a ray that goes through this, right, it'll only go through these pixels, right? The intensity of the at the entrance is is only for the first pixel. After that, there is some drop in its intensity, and for the second pixel, the intensity that goes into that second pixel is the output of the first pixel, and so on and so forth, right? So, and that comes out and comes to a particular detector. Early on, we had a simple expression like this, right? What will happen now is, in this particular case, your intensity of detection will be is, which is the intensity here, e power minus alpha 1 d1 plus alpha 2 d2 alpha n square dn square. So it'll be an expression, it'll have contributions from each pixel that it goes through. Okay, and if you again take the log, you'll end up with a bunch of equations like this. And these di to dn square will essentially be your columns here, or the rows, sorry, not columns, rows. Yeah, okay, that's all I wanted to say. There is just a couple of things that I still need to cover that we will do tomorrow, and then move on to the next topic. Yeah, okay, all right, thank you.